Yeah, the fission's just the splitting. And yeah, this is the most common reaction in terms of like providing energy because do you know how many different groups developed nuclear reactors independently? One. There's only the Navy. The United States Navy is the only one that's ever successfully developed a nuclear reactor. That's it. Done. Finished.
Wait, the Navy?
Yeah. That's why the nuclear reactor, as we'll see, is dependent on water.
How did that? Wait,
All of the carriers in the Navy are nuclear powered.
You're telling me the Navy were the ones who built nuclear reactors? Not anyone on the... Wait.
They're the only ones that developed the technology. Everybody else got it from them, whether they stole it, bought it, or bargained.
I always assumed that it was redesigned from nuclear weapons, like after World War II when we confiscated all the German scientists.
Nope, it's actually really hard. And the Air Force tried to do it. The Army tried to do it. Both of their programs, the Air Force's is awesome.
Yeah.
They did the molten salt thorium reactors, which are really cool designs. And they had a test platform that was producing 1 megawatt. But then they got canceled.
It's also not as practical, unfortunately, like the way that in use.
Yeah. I mean, you gotta remember though that the technology stopped being developed in the 1970s.
Yeah.
So like, the Navy one was only a little bit more practical at that time period, anyways.
Oh yeah, it's barely.
Yeah, and China has poured something like $10 billion into it. Okay. Oh yes. Can we? These discs. Got it.
Yep.
Hey, no problem. That happened. Okay, so anyways, let's go ahead and move on. We got chain reactions. And so a chain reaction is going to occur when a critical mass of, in this case, uranium undergoes fission. There's going to be a rapid increase in the number of high-energy neutrons available to react with more uranium. So to sustain the nuclear chain reaction, you have to have enough uranium-235 to create a critical mass. Now, they call this a critical mass. But I actually prefer the terminology critical density. Okay? That's so funny. So I prefer the terminology critical density rather than critical mass. And I'll show you why in just a bit. But so what needs to happen is you need enough uranium-235s around that first one that goes off so that it sets those off. Okay? Think of it a bit like this. Why can I light one match away from the pack without lighting up the match? The whole pack.
There's more mass in the pack?
There's more mass in the pack, but that doesn't actually affect, like, if I was to light that and then put it right under the pack, what would happen?
They'd catch fire. There's not a chemical reaction going towards the other matches, just the one that you lit.
Yeah, I'm not close enough, right? Yeah. It's a problem of density, isn't it? Of concentration. I don't have those other matches close enough to get set off. Okay? The same thing happens here. If the uraniums are too far apart, either because you don't have enough uraniums in the area to set each other off, or because they're too spread out, you can't get a chain reaction. Okay? By the way, this is why nuclear bombs, they do not set themselves off. Okay? There's actually been a case in the United States of us blowing up a uranium nuclear bomb warhead by accident. We misfired one of our rockets, this was a while ago, and it blew the uranium warhead up into the sky, and it landed outside the base.
The CEO on site must have been having a heart attack.
Yeah, I bet. And so they had to have the, I forget what they're called, they're the bomb disposal squad. Do you remember their name?
We just call them the bomb squad.
Yeah, they have a special name for the nuclear stuff.
Yeah.
But
If you have to call them, I don't know.
yeah, it's bad. And they had to show up and verify that this thing wasn't leaking and not gonna go off. And so, It does not go off. In fact, it didn't even get seriously damaged. They were able to recover it and then put it back in. They had to do a little bit of work on it, but yeah, so you need a critical mass that's together. How they actually store these before they're about to go off is that they actually store the uranium in separate pieces, or the plutonium if we're a plutonium bomb, in separate pieces. And that way we can never get a chain reaction. The worst that ever happens we get a leak of radioactive fuel. So, nuclear fusion, this is going to occur at extremely high temperatures, typically up in the 100 million degrees Celsius, combines small nuclei into large nuclei, literally fusing together nuclei, right? And it's going to release large amounts of energy. This is actually occurring continuously in the sun and stars. So when you look up at the sun, what are you admiring? A giant nuclear fusion, exactly. So it's a giant nuclear reactor.
That also reminds me of the second Spider-Man movie.
Mm-hmm.
They
Yeah,
be trying to make a tiny sun when they get going wrong.
that's true. Yeah, octopus. Yeah.
How valid the science of that actually is.
So the science of that one is kind of weird. But anyways, we can talk about it sometime. I'm actually going to show you one of the reactors for it in just a bit. So this right here is actually one of the fusion reactions. Up to the point that you start making irons, this actually releases energy. Anything after iron, in terms of nuclear fusion, actually uses up energy. So that's what kills stars and eventually leads them to explode. Is they get temperature differentials due to the fact that their iron cores start being a large amount of material. Okay? And that causes them to usually just have little collapses and eventually burn out. But if they're big enough, they can actually go boom. We call that a supernova. It releases so much energy in such a small area that it actually messes up space a little. And so it can make things like black holes.
And balancing, you would just balance it like the.
Yep. You would just balance it the exact same way you do all the others you got.
What will happen if somebody goes into a black hole?
You'll die.
You'll definitely die.
Okay.
You'll cease to exist on any level that we would consider you in any way. But you won't actually know it ever. So you will spaghettify first, which means that you start moving so fast that your light can no longer escape. And you reach speeds that are close to the speed of light, and you no longer can cognizate. So you'll spend essentially, for you, an eternity staring down it and going, "I'm going into a black hole. Holy shit!" Yeah. It'll be. It's really messed up. Yeah, like horrific. But anyways, it wouldn't really matter. You would die instantly. Your thoughts, though, would take a long time.
Spontaneously combust.
You don't even liquefy. At that, like, atoms don't even exist like we think of them at that level.
So basically, like, I will turn into a gas immediately.
You don't turn into a gas at all. You get crunched down really, really hard. Yeah. And so all of your atoms get fused into essentially a structure we're not quite sure what the hell it is. But it would essentially be like
Extreme torture method right there.
you wouldn't feel it.
Oh, really?
No, it happens so fast that you wouldn't feel it at all.
You could be dead.
As long as you can keep a mindset of this is kind of cool, it's a black hole, you'd be okay. The real nasty part would be the fact that your thoughts would start slowing down. And time would actually slow down for you. Yeah, time would stretch out.
Oh, that's weird.
Yeah, it's bizarre. Anyways, so nuclear fusion, this is a version of the fusion reactor. To be honest with you, at this point in time, any version of the nuclear fusion reactor I give you is kind of a BS thing. Okay?
Yes, they can't afford to actually put the spec for what it actually looks like out there because people might be dumb and try to make it.
Oh, no. They do all the time. The problem is that like, it's about every 3 weeks or so that there's a new record. And it's a almost complete redesign in some of these areas. And so I'm going to give you enough that you can recognize one day. But know that the shape may change quite a bit. Okay? There's a lot of development going on here. Big money. China has started pouring tens of billions of dollars into this. So we started pouring money in as well. Not as a country, actually as private concerns, which is pretty interesting. Anyways, this is a nuclear fusion reactor. Essentially what happens here is this is going to get so hot that we can't actually handle this with any normal materials. Okay? If you were to try to put this in an iron container, it'd melt and vaporize the iron. Okay? And so what you do is you take a very, very powerful electromagnetic field and you push all the material you want to fuse together, usually in a thin stream. But you can do it at a point as well. It's just harder to do. And so you then compress this, what's called plasma at that point. And that's going to be the compression plus the heat of it compressing is what sets off the nuclear fusion. Okay? Now, having said that, please note that we have not actually managed to be energy positive and sustain one of these reactions. We've been able to do one or the other. Okay? We're getting pretty close, actually. It's getting pretty close. But this is not technology you're going to see in 10, 20, 30 years. Okay? This is technology that if you start seeing this and getting power out of your outlet, this is going to be, if you're in the right place, maybe 50 years from now. If you're in the wrong place, it could be 100 years or more for rural U.S. Okay? This is not an immediate thing. So don't go banking on that to save all our asses. Okay. In nuclear power plants, the fission is going to be used to produce energy. The quantity of uranium-235 is actually held just below its critical mass. And you actually use what are called control rods to hold this. So you have individual uranium rods. They are below the critical mass. Okay. The control rods in the reactor are going to absorb neutrons to slow the fission process. Anybody tell me what those control rods might be made out of?
Uranium.
Yeah, you can just make them out of uranium-238. Spent fuel. Yeah. You can also use lead, and usually they go ahead and alloy the material to make them more resistant to corrosion and to make them a little bit more stronger and resilient. Because you really want to be able to control the control rods and not have them, bend out of shape. Okay? But, so the heat that's produced in the fission process is going to be used to make steam that drives the generator and produces electricity. Secretly, we have never moved beyond the steam age. Almost every single thing we do reverts back to steam at some point or another. So,
I think that might just be because we haven't moved past using water to cool things. If we did that, we might see the end of steam.
Yeah, I'm teasing anyways. It's there's no real reason not to use steam on a plant that's covered 70% with water, right? Or to really use anything other than water for most cooling, because 70% water. So it works pretty well. This right here is a nuclear reactor, by the way. This is why you never see leaks of nuclear material, and the outside of a nuclear reactor has such low radiation. So what you have here is a loop here. So right here we have the fuel rods and the control rods, and literally they're just interspersed between each other. And if you want the reaction to go faster and produce more heat, you pull the control rods out, right? So the reaction can go faster. When you want to slow down, you put the control rods in. Now, they don't have to have this little rod orientation. There's actually different designs you can make for this. But it's in a loop right here. So everybody see that heat loop right there? And what we do is we circulate usually water in there. Okay? Now, this water is at such high pressure and high temperature that it's not actually acting as a liquid anymore. It's what's called supercritical fluids, okay? It's kind of partially gas, partially liquid. It's a gas that's really condensed. It's a liquid that's moving really fast, okay? Okay, so this is going to be very, 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 very hot, right? And so what you're going to do is you're going to go ahead and put it into another loop. This is another heat exchange loop. This is going to boil the water in this container right here, and that's going to generate steam. That steam actually is what goes off to the steam turbine and turns it. And that provides the electricity. Okay? And then what you do is you bring this back down, you allow it to condense, and then you feed it back in. And so again, it's another closed loop. Everybody see that okay? Okay. And so finally, what you have is you have a water source. This is typically some sort of river, stream, ocean, something. The Navy originally planned for this to be the ocean under their boats, which is why it's totally dependent on having water that's cool to cool it. Because if anything happens on a Navy boat, what do? They just dump it out the bottom and
Pushed off the edge.
Yep. Yeah, they just dump it into the water with a chain on it and pull it back up when it's cold. And it works perfectly because, I mean, we're 2 loops out, right? We can't exchange anything from the inside to the outside anyways. So, yeah. So that's why the Navy never has meltdowns. It's because if they're getting close to having a meltdown happen, they just dump the thing off the side into the cold water and cool it down. And it can't melt down.
Must cost a rather significant amount of money, though.
Oh, no, they retrieve it.
No, it's not
How?
hard.
If it's, how?
You have,
They
you have
put a
on the
chain on it.
But if it's that hot that it's melting down, shouldn't it melt the chain?
Well, it won't get so hot it will melt the containment unless they aren't paying attention at all. By the time they throw it in the water will dissipate the heat and keep it from melting the containment and the chain.
Can they still use it afterwards?
Yeah, usually.
Yeah.
Because remember, they're monitoring it. So once it gets up to a certain temperature that anything could even be in danger, they'll dump it.
I feel like it might be easier just to design some sort of valve system that would intake water and pump it into.
They already have that.
the core.
That's actually right here.
Really?
Not in. No, you don't do it straight into the core, because if you do it straight into the core, you'd actually contaminate all of the water around you with nuclear waste.
Okay, well not the core, but like the parts that are overheating.
Yeah, that's the problem. Is you want these contained right here. That way, you can never have any exchange of nuclear waste. It's just such a bigger problem if you have exchange of nuclear waste. And most of this is metals that are pretty conductive anyways. So it's going to exchange heat with the outside very well, actually. Yeah. And so, yeah, they have had several incidents where the chain did break, though. So it does happen.
That's what they said on the Snoopy team.
They do, yeah. And we've actually had to retrieve one of these for Russia because it got too deep and they couldn't get to it. So it does happen. But yeah, this is actually where things typically fail in terms of ever since 3 Mile Island. So 3 Mile Island, that was a control rod failure. They messed up the mechanism of the control rod. It was not properly designed, and they literally just couldn't stop it from going. It didn't actually create a huge disaster, but yeah, it did create contamination. Fukushima, on the other hand, this is what went wrong. They had a bunch of huge earthquake, large tsunami. It took out their ability to cool the reactors. And so they dumped water on it, but they couldn't get it fast enough. Yeah. And so it did cause problems. So for each of the following, indicate whether it describes nuclear fission or nuclear fusion.
Nuclear fission.
Fission, you got it.
Large amount of energy is released.
Fusion.
Could it be both?
It is both.
It is both. Yeah.
Whether you're splitting or joining, energy is released.
Got it. Yeah, nuclear reactions in general produce tremendous amounts of energy. Small nuclei from larger nuclei.
That's fusion.
Fusion. Got it. Small to large. You got it. Yep.
Oh, okay.
Yeah. You're correct. Fusion.
I was like, okay.
Hydrogen nuclei react. Fusion. You got it. Several neutrons are released. Typically only fission. Partially because in fusion you typically have small nuclei. If you release a lot of neutrons, they won't be able to do that. You just don't have enough neutrons. But yeah, that's a typical mark of fission. Did I already talk about the only sources of energy on the planet? No? Okay. Can anybody tell me where does almost all the energy on the planet come from?
The sun,
The sun. Where's the second source?
the ocean,
The core.
Core?
The core, right? And then where's the energy for the core come from?
Atoms and heat.
magma,
It comes from the core, which has radioactive elements that are breaking down in it, which heats the magma. The magma system under the core does recycle that energy, and so it does heat up over time. But it's actually a nuclear reaction. So almost all the energy on the planet comes from nuclear reactions, whether that's fusion from the sun or fission in the core of the Earth. Does anybody know where the only non-nuclear source of energy ultimately comes from? This has to do with yours, the oceans. Not the cycle of water going up onto the surface on land is actually the sun, right? Yeah. So not waves technically, because waves are also caused by heating and cooling. Primarily the sun. Tides. What typically causes tides? The moon, yeah. So long ago, the moon actually hit the Earth. An object hit the Earth. It tore part of the Earth off, and that created the moon. And that collision is still bleeding off energy as it rotates around the Earth. Mm-hmm.
that's actually what also started life on our planet, because that object was like another similar size, but not quite a sister planet, kind of called Theia.
Though the life being started on the planet due to that is unsupported. But yes, you were right about everything else on there.
But set in motion the events.
It happened quite a bit before life actually started populating the planet.
Yeah, but it was like what set it off.
It did help the cooling process,
Yeah.
which was necessary for life to develop on the planet. Mm-hmm.
Is there any way to like prove that the moon came from the Earth?
Yeah, we have actually taken rocks from the moon and compared them to rocks on the Earth, and they have an extremely similar composition. Yeah, and there's actually objects on the moon that almost certainly came from Earth. There also is objects that are not similar to the Earth on the moon, but we've only had a few missions up there to gather, so yeah. That's one of the reasons we want to go back, is because there's some theories that have developed since, 30 years ago, 40 years ago. And people are like, we could really use to test some of these. But, so let's supply the missing atomic symbol to form the equation for the following nuclear fission reaction. So what is this? Right here. So what's the first thing you do with these? You always take top and bottom and add them together, right? Yeah. Okay. So go ahead and start writing it out. I'm going to quiz you.
Oh, I don't know this.
You do.
I didn't catch on it whenever we did it.
So just take the masses. The mass on the left side has to equal the mass on the right side.
Okay.
So if you add everything over here together, it has to be equal to here. you can work with your partners a little bit. I'll be doing a quiz thing in a little bit, so don't forget to bring out some device to do the QR code and answer the question.
Okay.
Okay. All right, we're going to go ahead and move forward soon. We're solving for that question mark. That means an atomic mass, an atomic number, and then a symbol, right? And we will be registering for a quiz in just a bit, and then answering that quiz question. So go ahead and get prepared. Okay.
Is it 141B?
Okay, I'm going to go ahead and move forward. Okay. So go ahead and get registered.
Same.
Okay. Yeah, it's funny because the thing detected you guys twice the first time versus the second time. Yeah. All right. You ready?
No, this won't scan. Hold
This right?
It should be. Just make sure you get to the quiz here.
The Q&A?
It's the
on.
quiz.
Makes sense. Okay.
Yeah, looks like I'm there.
Yeah, it'll pop up when I go to the next thing. Okay, everybody ready? Fantastic. Okay, so supply that missing one. It's one of those options. Click on one of those options.
Yeah, so you can go.
We get bins. Is it
Nope.
gonna be something that's been used before?
Huh?
Is it gonna be something that's been used before?
No, you can get it from that prompt. Just using what we've done like 4 times before in the previous questions.
Dr. Clausen,
Mhm.
question. So on the problem,
Mhm.
you see the 2 in front of the 1 over 0. If you have to multiply it, why don't you just put it as 2 over 0?
Let me go back to the symbols and we can.
Okay.
Okay. Okay. I'm gonna go and go forward. So make sure you got your answer in. Okay. Ready?
Yeah.
Okay. I'm going forward. Okay. So that was the majority of the answers, and that was correct. Okay. Now, like you know, I'm going to. I'm always going to go back to the problem. Okay. So what do we do for this problem right here? Well, we just add up each side, right? So on the masses on the top, for the left side, we go 1 plus 235. That is, yep, 236. Okay. And on the left side, we go 137 plus, and then it's plus the 2 and 1, right? So 2 times 1, which is 2. Okay. Was that what you were asking there?
Yeah, so why wouldn't we just write it as 2 over the 0 because 2 times 1 is 2 and 2 times
Because then it wouldn't be a neutron.
Okay.
It would be some weird particle with a mass of 2.
So that's telling me that it's the neutron.
Exactly.
Okay.
That's telling you there's 2 neutrons versus whatever a mass 2 neutron would be.
That makes sense.
Yeah. Which is not actually a particle that exists, but yeah. And that's why we do that for every chemical formula, is because the identity stays the same.
Okay.
So it's like saying 2 hands versus 10 fingers. Yeah.
Okay.
Okay, and so our mass right here is 139, right? If we take the difference between those, what would that be?
97.
97, you got it. And so the mass of our unknown is 97, isn't it?
Between the question, difference between the 236 and the 139?
Yeah.
Okay.
Yep. Okay. And so the next thing we're going to do is we're going to take the atomic numbers and add them up, because those account for charge. And we're going to go 0 plus 92, and that is 92. You got it. And on the other side, we go 52 plus 0 times 2, but that doesn't matter. And we end up with 52. We take the difference between those, and we get 40. You got it. Okay. And then what's the last part we need to do?
Find it on the table.
Yep, we need to go up to the table and find it. Which one's 40 on the table? ZR?
Yeah, I don't know the other one.
And then take
Okay.
the 97.
Yep. Yep. And so the 97's on top, the 40's on the bottom, ZR. I went ahead and put it in a slightly different format, didn't I? Okay. Okay. Note that all of these problems for all the nuclear reactions are just like that. They're the exact same thing over and over. They're not really any more complex. You just keep doing it until you got it. Okay? Doesn't really matter how many things they add to it, because it always has to be the same on both sides. So, all right, let's go ahead and go on to the next one. Okay, chapter 6.